Hello. So in this lecture, we're going to be looking at how we can do breast cancer prediction with neural networks. So the idea here is that we'll be given a breast cancer prediction dataset, and by that I mean we'll be looking at characteristics of cancer cells and determining whether they are malignant or benign, where malignant means that they are infectious and benign means that they are not harmful. So the goal is to look at the characteristics of cancer cells and determine their class, whether they are, if the class is 1, it means they are malignant, and if the class is 0, it means they are benign. Right. So we're going to be creating a model that would look at those characteristics and make the appropriate classification based on what it learned. So before we actually get started at building the network itself, we need to note down the steps we need to take in order to undertake a task like this or any other machine learning task that we may undertake in the future. So the first thing is we need to define our features, in this case the characteristics, and labels, right? So we already know what our features are and we know what our labels are here. We're going to look at this in more depth when we look at the data set itself. So we need to define our features, when we need to define our labels. And the next step, we need to define the training set. So that's the training set and test data sets. And the reason for this is the training set will be the data that we learn from, right? And so let me actually illustrate this here. This is the set that we learn from. And this is the set that we evaluate on the test set to ensure that our model is performing reasonably well, right? That's why we need to separate these two. Or things such as overfitting might happen, and we'll discuss those in more depth in future lectures. But if you're curious about it right now, I also have a statistical machine learning course, or Bayesian machine learning course rather, that is going in depth about what overfitting is and how to prevent it and so on. So after doing this, after defining our training and test data sets, we need to define the model architecture. So we need to define our model architecture. So what do we mean by model architecture? Well, like how many layers our neural network is going to have, say how many neurons, and so on, things like this, right? We need to also define this, and we need to define, let's say, our activation function. So last time we presented the sigmoid activation function, but there are many activation functions we could use. So just to give an example, we could use something called sigmoid, we could use ReLU, and they all have their advantages and disadvantages, and they all have problems in which they work better in. But again, this is something that I will leave for future lectures. And the fifth thing we need to define, so we have a model architecture now, we need to define our loss function. So we mentioned it before that we have loss functions that are appropriate for different problems. So if it was a regression problem, maybe we want to use the mean squared error, right? But since here we're doing a classification problem, maybe we want to use like a binary cross entropy loss function. Again, we didn't discuss what that actually is yet, but I am saving that again for lectures in the future. And finally, let's say after defining our loss function, we need to also define our hyperparameters, right? So we need to define something like what is our learning rate, which we talked about in the last lecture. And we need to define, say, our optimizer. So optimizer would be like, are we doing gradient descent or are we doing something else? And so on. So this is it. And then finally, we need to define the evaluation method, right? So here in this particular lecture, we're just going to compute like a straight up accuracy, but we can also look at other things like precision, recall, and so on, or F1 score. Like there are many other measures of evaluation that we could make. But in this case, let's just stick to the simple stuff, because the goal of this lecture is just to help you define a very simple neural network for a very simple data set. And from then on, we'll start adding the complexities as we go on. So let's actually take a look at our data set. So this is our data set. And in this data set, we're given a couple of things, right? We're given our target, our label, where 0 means that it's benign and 1 means that it's malignant. And we're given a bunch of features like mean radius, mean texture, mean parameter, and so on. So that means if something has the features 17.99, 10.38, and so on for mean radius and mean textures and all these other features, then its label is benign. But in this case, where the mean radius is 7.76, 24.54, and so on, the label is, well, the label in this case is malignant. So let's actually do that. So we define our labels. So we look at this entire vector of labels and we call it y, right? And then we look at our features. So this is, let me use a different color. So this is y, which is our label. And then our features are x1, x2, x3, all the way up to xn, right? So we can consider this entire matrix of X to be our feature matrix. So we call our feature matrix X, right? This entire feature matrix. And we call our target vector Y, right? So we call this, okay, this looks more like gamma, but you get the point. So we have our feature vector and we have our target, right? We have our target Y here. So the next thing we need to do is actually split this into two. So from this data set, we're going to use some of it for training, which means we're going to learn from it, and we're going to use some of it for let's say evaluating how good our model is, right? So let's say we take something like 70% of our data, right? We take like, say 70% of our data and call this our training set. And let's say we take like the remaining 30%. And of course we should be doing this, we should be choosing this randomly to avoid any bias. And we call this our test set. So we have our training set and we have our test set. In our training set, we have our features and our labels. And in our test set, we also have our features and our labels, right? So we're going to have X train, right, from our feature matrix X. So X train will be corresponding to, say, this 70% of our features here, right? And we'll also have, let's say, Y train here. So X train, Y train, and then we're going to have X test and Y test, right? So again, X test is the remaining 30% here, and Y test is the remaining 30% of the labels. So what's gonna happen here is that we're going to take X train and Y train, right? Which means this is 70% of our data set, and we're going to learn from this, right? And what we're gonna, and the way we're going to evaluate is we're gonna take X test, right? We're gonna feed it to the model, right? And it's gonna give us some predictions. Let's call them Y predictions. And then we're gonna compare this. We're gonna compare these predictions to Y test, right? And using this, we're gonna compute our accuracy. That's the idea, right? That's kind of like the pipeline we're following. So with X train and Y train, we're gonna do the steps that we discussed before, whereby we will be learning from them, we feed them to the model, we do gradient descent and so on. We compute our weights and all that, and we're gonna get to that in a moment. But for X test and Y test, we only use this at the end in order to evaluate how good our model is. So here we're just keeping things simple by using a training set and a test set, but there's this phenomenon that we already spoke of called an overfitting, whereby we could split this into 3 components where we have a training set, a validation set, and a test set, and so on. But for this lecture, we'll just keep things quite simple and stop it right there. So let's look at the code itself. So essentially, we're going to use the Torch library, right? We don't actually need to use the pandas library here, but in any case, if you want to have a better visualization of the dataset, you could. And then we can use sklearn, right? So the part that we need to focus on here is that we're going to have X train, X test, Y train, and Y test, right? We're going to create this data set, and here they are just NumPy arrays, right? Or matrices represented in NumPy. But in order to feed them into PyTorch, we need to use something known as a torch tensor, right? We need to convert these NumPy arrays into a torch tensor, and we need to feed it into a tensor dataset and create what is known as a data loader, which allows us to essentially load our data in batches, right? So that means every single time that we're training, we load a batch of, say, size 50, and then we compute our gradients and everything just on that batch, and so on. And there are advantages of doing things this way, but for now, there's no need to focus on this, because this is all material that I'm going to cover in a future lecture. I'm going to have a separate video at some point of this PyTorch operations if needed. But for now, I just want you to get the main idea about how, when we're given a data set and we split it into X train, X test, Y train, and Y test, and using that, we just feed it into what's known as a train loader and a test loader, which are just data loaders in PyTorch that help us do the training of our algorithm. So let's actually look at the model architecture, right? So we're essentially finished with the step of defining our features and labels, where we said our features and labels are going to just be defined by x1 to xn and our y. And then we said we're going to define a training set that we learn from and a test set that we evaluate on. And we saw how we can do that here, right, by splitting train and test. And here I'm just actually using a function from sklearn that just splits it for us. Like, let's say our test size here is 33%. So that means like 33% of our data is going to be used for testing, or the remaining 67% is used for training, right? That's the idea. And now we're moving on to defining our model architecture, right? So let's actually define how things are going to flow from here. So essentially what we have is, well, we're going to input our features that we spoke of before. So we'll be inputting here, let's say x1, x2, x3, x4, x5, x6. Okay, in this example, there are only 6 features, but in our case, we'll probably need to have an input layer for the whatever number of features that we're using, right? So that's fine. And then we're gonna have a hidden layer here, another hidden layer there, and an output layer. So the idea is that we feed in these features, right? These are features. And this is when we're doing training. We feed in these features. And after feeding in these features, what we do is they go through the neural network and we come out with some prediction, right? Say we come out with some prediction, y bar. Then we compare it with the actual value. And then if there's a difference, we're going to propagate, we're going to actually differentiate the error with respect to the weight values, which we talked about in the previous lecture, and do back propagation. And after that, we're going to continue this process using maybe gradient descent until we reach a point whereby we minimize our error and we're able to make a model that can accurately create these predictions. So for that, again, let me just make that clearer. The first, let me actually write this and say we're gonna feed in our features, right? And then we're gonna get a prediction. We're gonna define our weights. Initially, our weights, let's say this is W, say WN, right? And initially these weights are random, but we want to have those weights take values that enable us to make more accurate predictions. That's the goal here, right? And we discussed that in the previous lecture, so I'm not gonna go through it again. But first of all, let's actually look at how we can define the network. So first of all, we need to say how many layers are we gonna have. So here you can see I have a simple neural network, a simple feed-forward neural network, right? And we're gonna have layer 1, layer 2, layer 3. So what layer 1 here is taking is an input dimension, right? Here I just put 1, but this depends on how many features you have. So if we have 6 features, this should be 6, essentially. That's the idea here. So the input dimension, and then this 16 is showing how many neurons we're going to have in this first layer. So in this case, it's 12, but this can be as many as you want. So let's say there are 16 of them. And then this is showing okay, for the next layer, how many neurons do we have? So here we're going from a layer with, let's say, 16 to a layer with, let's say, 8, right? So then that means that this is 16 to 8. And then finally, it's 8 to output dimension. So this is from a layer with 8 neurons to a layer with a single neuron, right? So that's 8 to output dimension, which is 1. So it's very simple to create a neural network. All you need to do is define, say, okay, I'm going to have 16 layers, and then 16 to 8, 8 to 1. That's it. It's not that, it's not difficult at all. I mean, in this case, of course, we have 12 layers. So if you want to use 12 instead, just change this to 2, and change this also to 2. And that should be fine, right? Okay, so we've created our neural network, but we want to define what we called forward propagation from before. And what we said was that essentially each and every one of those neurons is going to have a sigmoid function. That's what we defined in our last layer, or an activation function in general. So we are at this point where we're defining our activation function. We're just choosing the sigmoid function. So this is essentially defining the order of operations, right? So first of all, we get x. X is just our input or our features, right? It's just representing this over here. This is x, right? And the first thing is x is going to go through L1. So it's going to go through this. It's first going to go through this, right? And then after going through this, we feed it into an activation function. We use a sigmoid function. So we apply a sigmoid function after feeding it into the network. And then after that, we feed the output of that into layer 2. and we feed the output of that into layer 3, right? And the output is finally whatever the value is. So if you remember the sigmoid function, it looks sort of like this, where this is 1, this is 0, this is 0.5. And we said that in our case, like if we put it in the final layer, that means the output is going to be a probability of it belonging to a certain class. So we're going to look at this further when we look at how we are making our evaluations. But just note that the output here is going to be a probability. So if it's like 0.99, that means there's a 99% probability that based on these features, this cancer cell is malignant. If it's 0.32, it's like the 32% probability that this cancer cell is malignant, right? So we can set a threshold of saying that, okay, we're going to set a threshold of if it's above 0.5, we just say it's malignant. If it's below 0.5, we can say it's just benign, right? So that's how we define a simple feed-forward neural network. Again, it's very simple. We just need to, like, if we have in our mind what architecture the neural network is going to take, then all we need to do is just use this nn.linear function and say, okay, from input dimensions, I'm going to have 16 neurons in the first layer, and then 8 neurons in the second layer, and then my output neuron is going to be just one dimension. That's it. You already defined your simple network, and then you're going to define the order of operation and go like, okay, I'm going to use the sigmoid activation function for each and every neuron, right? So in this case, that means for each and every one of this, there will be a sigmoid activation function. And also for your output layer, there's going to be a sigmoid activation function, which gives you the probability that this particular, example belongs to a malignant class or a benign class, right? That's the idea here. So let's look at how we will do our training, right? So the idea now is that we define a training function, right? So we have defined our neural network. We have talked about our data set, and we saw that it's simple to create this network. And we just need to create a procedure for training, right, our network. So for that, let's first remember once more. Let's say we have some weight Wn, right? The idea here is that if we define our loss function, right, and loss function, last time we were looking at MSE, we can use binary cross function, doesn't matter. Like the point here is that we have some loss function. And with that loss function, we compute an error, E, right? And we said we would want to take the derivative of that error. Let's say we want to update the value of this weight. We want to take the derivative of that error with respect to Wn here, right? And this is what this is how we compute the gradient for this, right? And we also want to, let's say we have Wk over here. We want to take the derivative of the error with respect to Wk. And the way we would update these things, we would say, okay, Wn is equals to Wn minus alpha, some learning rate, times the derivative of the error with respect to Wn. Or we say Wk is equals to Wk minus alpha times the derivative of the error with respect to Wk. So this is something we looked at. So if this is not making any sense to you, just look at the previous lecture when we introduced the idea of backpropagation. And we say that the way we learn, right, because initially our weights are going to be random. So since our weights are random, we want to update them to like more accurate values. And the way we update them is first by computing the gradients. So we compute all these gradients for all these different weights, right? And then after that, we need to make the update. We need to update our weight values, right, based on the gradient. So, and we talked about how we can do this using backpropagation in the previous lecture. But now that we're doing this in PyTorch, so we need a method that just computes these gradients for us, and also a method that updates our weight values for us, right? So PyTorch provides those functionalities. So the idea here is that, okay, we feed in our model, and the model is what we defined here, the simple net, that's our model. And then we have a train loader. And then the train loader was the output of this when we're creating our data set, and it loads our data set in batch size of 50, right? And then we have an optimizer. So in this case, we're gonna use, we can use what is known as stochastic gradient descent, we can use Adam optimizer, and so on. So there are different kinds of optimizer we can use in different problems. But you don't need to worry about that right now. And here with us, we have a loss function, and we defined, like we said in this case, we're going to use like a binary cross entropy loss function, right? So the idea is, first of all, we call model.train, right, to signal that we're about to, we want to train algorithms. And in this case, and of course this also sets our requires gradient to true, but like we don't need to, actually, yeah, I'm going to discuss the how this functionality works in the future, because that might take some time here. So the idea is now that we take this train loader, right, and then we get, from it, we get X and Y, right? So this is essentially X train and Y train, right? So the first thing we do is we set our optimizer to 0 gradients. We zero out the gradients to prevent the accumulation in each batch. But what we need to focus on is here. We feed in X, we feed in our features. Here, the features that we defined here, we're now feeding them into the model that we defined here, right? We want to feed those features into the model. So we say the output is equals to model, and then we feed in our features X. And then the next thing is to compute the loss, we need to compute the loss of the error. And the error is computed between Y, which is our target, and output, which is our predictions. So output here, again, is referring to our predictions, right? So output refers to our predictions. And then we compute the loss between the output and the predictions, right? So don't worry about those terms like view minus 1. This is just reshaping the tensor. For instance, if it looks like this, 1, 2, and so on, if you call view minus 1, it will just make it a one-dimensional vector like that. So that's what this is doing, but you don't need to worry about this for now. The point is that we need, into our loss function, we need to input our output and our targets, right? And now that we input our outputs and the targets, like I said before, the first step is we need to compute the gradients, right? And to compute the gradients, we call loss.backward. So this computes the gradients for us. And the next thing we need to do is we need to update our weights here, right? And in order to do that, we use this function, optimizer.step, right? So these are the main things you should focus on, right? So there might, if you are confused right now, just to make things clearer, like we're going to dive into some of these functionalities later on, but all you need to know is how you can use this data set to split it into your train and testing set, how to create a neural network, and that part should be very simple. How to define your activation function, also very simple. And the main thing you need to focus on is you get your predictions by feeding your features to the model, right? You feed in your features X to the model, you get your predictions, right? And then you compute the loss, right, by inputting your predictions and your targets. And then from this loss, what we need to do is we need to compute the gradients. And to compute the gradients, we use the function loss.backward. And then we need to update our weight parameters, and we use optimizer.step. And that's pretty much all you really need to know. And then, so this is when we are training. And then when we're evaluating, essentially what we do is we feed in, again, we feed in our test features, so X test, that we get from test loader. We feed this into our model. We get our output. And then let's say we have our predictions here, we have our targets. So we say when the predictions are greater than 0.5, then we call that as malignant. Otherwise, it's benign. And then we check the accuracy by see where the predictions and the targets are pretty much the same, right? So it's just a simple operation. So let's actually look at the code itself running. Okay. So first, we have our model. We already said what that is, right? We defined our model here. And it's the same thing as you saw in my explanation from before. And then this is for just creating our data sets. So it's called load data. And then this is where we're just training and just making an evaluation and so on, right? So I've already explained the training function and the evaluation function. So train loader and test loader, we know what those are. The model is the simple neural network. Our input dimension here is just 30, so that means we have 30 features, and output dimension is 1. The loss function we're going to use is called the binary cross entropy loss function, and the optimizer here we're using is the Adamo optimizer. We can also use like the SGD optimizer, which means stochastic gradient descent, and so on. So there are all these different optimizers here, as you can see, that we can use, whether it's ADA grad, ADA delta, and so on, right? So that's the idea here. And then for epoch in range 200, so we're going to train our model, right? So in this, when we're defining our optimizer, we need to specify our learning rate. So if you want to know when you specify the learning rate, you specify it when you define the optimizer here. So for epoch in range 200, we're going to feed in our op model, right? SimpleNet, which we talked about. Train loader, we already talked about this when we're creating our data set. Optimizer, we talked about this, the different optimizers. We're going to use gradient descent, stochastic gradient descent. We're going to use Adam and so on, right? These are things you can experiment with. And then we define our loss function. Let's say we use binary cross entropy loss function. If we want to use something different, we can use MSE and so on. And then just the epoch, which is just what iteration we're on. And the idea is that we just need to make sure that the loss is going down. And in the end, I'm just printing out like what is the accuracy of the model by feeding the model and the test loader into our evaluation function to see how well it is performing. So what we do is we call, let's say, Python train, right? So this trains, and let's say at the end our accuracy is 95%, which means the model is performing decent enough. But the idea here is that the loss starts as being quite high, and it should just continue going down and down and down to show that we're actually minimizing the error and so on, right? And that's just the basic idea. So this is a very simple problem. Like the problems that you encounter most of the times are going to be more complicated than this, and they're going to involve like much more operations, much more like hyperparameter tuning and so on. And we're going to look into how we can solve those problems later on. But here I just wanted to show how we can build a very simple neural network so that you familiarize yourself with like the most important operations in defining just a simple working neural network. And then later on, we can talk about how we can make more, let's say, nuanced or like more complicated networks that will solve more complicated tasks, so to say. So having said that, I'm going to stop here. So thank you for your time, and I'll see you in the next lecture.